first time in this building. So it's really special. So I'm Arindam Ghosh. I'm from physics department, same department as the previous speaker, and we work on very similar things. So, but I'm going to give you a little more experimental aspects of some very recent experiments which we just finished actually taking the data and analyzing. So it's not published, but I thought this will be an ideal opportunity to share the results and see if some discussions can be started. Okay, I'm going to make a small change in the title. It would be on bilayer graphene, because what we have done over the last few months, and this is the work which is primary thesis work of Ali Amer, who is going to finish his PhD probably in next month. So if someone wants very excellent postdoc, he's the one. And also, I would be very, I must mention Professor Rajdeep Sharma, co-organizer, and we have been talking about this result time and again with him. He has been our theoretical support. Okay, so what I'm going to say is what kind of topology, what's the specialty of bilayer graphene that we're looking for, and I'm going to tell you, in order to access those topological properties, what special arrangement that you have to make to access in terms of device structure to get those topological properties. And then I'm going to show you the results which we now are starting to write up. Okay, so we all know what bilayer graphene is. To this audience, I'm sure by now bilayer graphene is clear. There were talks. It's nothing but two graphene sheets which are slightly shifted from each other. And the advantage is that if you apply an electric field across the plane of graphene, of this bilayer, then you remove the inversion symmetry, and that leads to an opening of a band. So that's one of the most interesting aspects which got bilayer graphene the first publicity, so to speak. And I think this paper from the Delft group was very early days of 2007, 2008, which showed how a band gap can be opened in graphene, leading to some form of a variable range hopping transport at very low temperatures. So this was original interest, why bilayer graphene came into picture, because you can open a band gap and hence get very high quality transistor actions. However, that's only the start. And then people realized there is much to bilayer graphene than just an opening of a band gap. So if you look at the standard, by now accepted Hamiltonian for bilayer graphene, you see that it's very similar to single layer graphene, except for the fact that, in the sense that, of course, the charge carriers are still chiral, like single layer graphene. But here, the pseudospin that one is talking about is not the two sublattices, like in the case of single layer graphene, but it's the layers. Because the system exists in two layers. The low energy Hamiltonian is formed by an electron in the upper plane and the lower plane. So you have a pseudospinner essentially creating the eigenstates are a superposition of two states in two different layers. So that leads to very similar physics. The physics is qualitatively at that level similar to what single layer graphene would be, and leads to similar to topological insulators, pseudo-spin momentum locking, and similar kind of topological charge that you would see in topological insulators. This led to two different types of phenomena, and that's what we are looking for. One is similar to a spin Hall effect. We now have Valley Hall effect because we have replaced the standard spin by the pseudospin, and that led to some interesting series of theoretical suggestions and experimental verification. I'll show you in a slide. And also, because it is something similar to a topological insulator, the bulk edge correspondence tells us that if we can completely gap out the bulk of the system, we should in principle be able to get an edge current moving. It's not just an edge current, but it's an edge current which will be supported only if the bilayer graphene is terminated by the zigzag edge and not the armchair edge. That's very important to understand. By the way, we'll go to this. This is the topic of today's talk. Okay, so just about late last year, two back-to-back papers came out in Nature Physics, which showed for the first time how to access Valley transport, or similar to Valley Hall effect in bilayer graphene, by opening up a band gap in graphene with a very strong electric field. I'll just spend a minute or two in this. This is also an aspect of topology in bilayer graphene. So let's understand a little bit about this. So what they did is essentially opened a band gap like this, and then because of the Berry curvature, the Berry curvature makes two valleys, K and K prime, move in opposite direction when they're injected. And that's exactly what happens. If you inject current in this direction, the electrons or the holes, which are, when they move in both the K and K prime move in opposite direction, and that eventually leads to an accumulation of additional charge in a different contact. And when I measure the potential across these probes, I measure a potential which is away from where I injected my charge from. So this is what you call a non-local measurement. And this non-local measurement is very typical for spintronics, because that is how we first measured spin Hall effect, where, of course, it is the spin which is protected by time reversal symmetry led to non-locality. But here, it's actually the Berry curvature. Okay, so this is how it's measured. What it needs is a band gap at the Fermi energy, and leads to what you call as Valley Hall effect, or Valley Hall conductance of 4e squared by h. I shall not go into that detail. But this is the experimental result. It showed that when you have a gap opened up in these kind of geometry, you end up getting extremely large non-local resistance, primarily because the electrons have moved from here and then accumulated preferentially in one of the probes rather than both probes. So this has been established and experimentally verified. Problem is, what's about the other part? Why are we still not seeing the edge transport in bilayer graphene, which had been so easy to see in case of a standard topological insulator? The reason behind it is the nature of the pseudospins are very different. In the case of standard topological insulator, you need to incorporate a time reversal symmetry breaking phenomenon to actually destroy the topological effects or the edge currents. Over here, it's actually very easy to break the symmetry, because here, if I have a sharp edge, sharp defect along the edge, then what it will do, that it will mix the K and K prime valleys, and hence any kind of edge states that otherwise flow without any dissipation now gets dissipated or localized. That's the difficulty experimentally had been for a very long time to access edge states in gapped bilayer graphene. I'll show you how we solve that problem today. Okay, so this had been theoretically discussed for a while now. So this is a topological origin of subgap conductance. What this theoretical paper showed, that even if you have some disorder along the edges, where you remove some of the zigzag and convert it to an armchair, you still can have some edge transport. If you have perfect zigzag edge, your net conductance of the edge will now be 4 times e squared by h, where 4 is 2 from spin degeneracy, and because you have got 2 edges, you have got 2 additional numbers, so the total conductance will be 4 e squared by h. What the theoretical calculations show, that if you now have strong disorder at the edge, then you'll see that the conductance is exponentially decreasing. L is the length of the edge, and D is the depth of the disorder. And as you increase D, your conductance is going down, but it goes down exponentially with the L. Okay, so this is the key difficulty. These are key difficulties are uncontrolled experimentally when we make bilayer graphene. The edges that we create are mostly, we have no control on the edge, what kind of edge it comes. And also when we make devices out of it, we normally chemically destroy damage the edges. So we don't have a control on whether it's zigzag or armchair. Environment contributes hugely to disorder. So bilayer graphene itself is a disordered quantity, and it sort of has a long band tail, which is a problem. I'll show you in a minute. And also the kind of techniques we use to probe the to these edge states may not be completely adequate yet. Solutions, and that's what we do, is that first we will make sure that the edges are chemically pristine, and I'll show you how to do that. And second, I'm going to use short channels. I'm not going to go very long, and the longer you make, the more susceptible you are to result. And third, I'm going to go large band gaps and see what happens. Okay, for those who are experimentalists here, I'm going to give you a very quick review of what has already been said, and this is exactly what we do. We open a band gap and we put two gates along the band graphene, top and the bottom, and then what we can do using the two electric fields, we can control the Fermi energy and the band gap independently. So these are easy thing to do, and these are well-known independent control of density and the electric field, which electric field opens the band gap, which simply by multiplying by the thickness of the bilayer. So I'm going to give you a very short tour of how we make these devices. We take graphene, which is exfoliated on, first we take a boron nitride strip, which is insulator, single crystal, and then we pick this up using a polymer, and then we take out another graph, which, now this is a picked up graphene, which is observed through this microscope, and then what we take a bilayer graphene, which is exfoliated separately, and then we pick that up using the boron nitride. So the bilayer graphene does not see any kind of chemical impurities anywhere, and then the whole thing then goes and gets deposited on top of a silicon oxide substrate. So when this entire thing is done, you see this is how it looks like. This is a bilayer graphene which is covered entirely using boron nitride. So the edges are technically pristine. There are several types of devices we make here. I'll just quickly go through what we do after this is we etch it down, this boron nitride here, like this. And then, by the way, by we, it means Amir. I don't do anything. So then what we do here is, or Amir does here, is contacts. And this is now contacting the side. This is the source and drain. And then you put gates on top. So there are suspended gates also, but mostly we do the edge contact. This is a typical device that eventually looks like this. These are contacts, these are gates on top, and there's a global back gate at the bottom. So these are the two gates. This is one of the device characteristics. Those who are experimentalists will understand this is actually a very high quality device. You can see the resistance is changing by nearly 4 orders of magnitude by applying an electric field, which means that at the Dirac point here, there's a large band gap has been opened up. And this line is nothing but how the the charge neutrality point at this point moves as you change the top gate and back gate voltages. So this line is essentially the n equal to 0 point. Now once you have that, you can immediately find out what will be the points where the density is constant and only the electric field is changing, which is nothing but a transpose of this equation. So these yellow lines are my locus of gate voltage, the top and the bottom gate voltage, along which I can keep my density fixed, only change my electric field. And what Amit did is essentially go along this line where I'm sitting right at the charge neutrality point or the Dirac point and changed the electric field on the bilayer graphene. So that's important, that we are always at the charge neutrality point. So I'll show you 7 samples. This is actually the painstaking experiment. There's 7 different experiments done. What we have done is we have used very, very short channels of approximately a micron or 2 microns rather than tens of microns. Also, the width is smaller, the length, the aspect ratio vary. Typical mobilities are not great because of the contact resistance, but the characteristics are very similar. There's a reason why I colored these 2 separately. I'll come to that later on. Let's see how does the electrical conductance vary as a function of the electric field when my Fermi energy is right at the charge neutrality point. You can see the electric field is increasing, the band gap is increasing, the conductivity is decreasing. That's great. And this is in E squared by h. This is conductance, by the way. We have not normalized it with the area yet. What I can do now I can actually go to large values of D and then try to extrapolate. Okay, this is one sample. Let's try to see what happens in the other samples, one by one. This is a second sample, which is again a short one. And if I extrapolate it back to 0 electric field, from the value of high electric field, it starts hitting the same point. This is the third sample. This is the fourth one. This is the fifth one. So almost all devices, what's happening here is that when you go to large electric field and the conductance is decreasing exponentially, I take that regime and extrapolate it back to 0 electric field. I tend to hit the value of 4 square by 8, give and take plus minus 1 if you're unbiased, and I'm going to go somewhere here. So the question is whether this is something common to everybody. So it turns out that 2 devices we got where we could not fit it. Actually, you can see this device. The red one is essentially a very short device, which is 0.6 micrometer. We do not really know what is happening. The blue one, it's a very long one, and then we essentially did it again and found that this also probably will, if we go to high value of electric field, probably we should be able to get a very similar kind of asymptotic behavior as we saw in other devices. So if it is conductance or conductivity, we find that once we divide the conductance by the aspect ratio, because L and W are changing, we do not really get a very high convergence of the prefactor. Okay, so what's possible here? I mean, why is it, what's happening at low electric fields and what is happening at high electric fields? Now we all take this particular example of one of the devices, and look at the low values of electric field. Now if we had a perfect bilayer graphene, in which case the density of states in a band gap would have been like this, which is great, but it never is like this. So it's imperfect. So there will always be a broadening of the band tail, and that band tail will move into the charge neutrality point, and that means that in this regime, even if we are sitting at the charge neutrality point, we still have a significant amount of bulk contribution in the transport. And not just contribution in terms of a parallel contribution. We are not saying that okay, there's a channel along the edge, and there's a channel along the bulk, and so okay, you should be getting something which is smaller than the total conductance. Probably, or larger than the total conductance. Probably what is happening is that there is a significant of hybridization and leading to bulk and edge getting mixed up and leading to completely different conductance values. So this is why once you start only getting the band gap higher and higher, you start seeing the effect of the edge, and this is the region where, and which electric field this region commences from is a very device-dependent phenomenon. It is, so for some devices which is more disordered, this will come at a larger value of electric field. In some devices where the system is less disordered, this regime starts earlier at smaller electric fields. It obviously depends on the extent of broadening of the bands. Okay, so we ask the question then, okay, so this is the regime probably where the transport will be primarily along the edge. Okay, so can we understand this in terms of if we consider this is an edge transport? So from computational point of view, and probably intuitively as well, we probably have an edge transport, but now, because of the edge disorder, we have removed some of the parts of the localization. These are localized edge states where localized throughout at very points. So the total conductance now is no longer perfect 4e square by h, but essentially exponentially limited from that value of length of the edge divided by the localization length. If we assume that the localization length is inversely proportional to the band gap, now this is an assumption, it's up to criticism, but in many cases it's actually 1/root of band gap, but it's, at the end of the day, we are just trying to understand if a model fits it. But if I take a localization length is 1/EG, where EG is proportional to D, then we do end up getting something which explains most of it. So then we asked the question, okay, fine, we are getting something there, but is this really a topologically protected edge-state transport? And just by extrapolating the conductance, it's almost never enough. You are fine, we are getting some nice convergence towards 4e square h, good, but we would like to come and ask the question from the other direction. If this is a topologically protected transport, how we can verify it? One of the ways of verifying probably would be mesoscopic fluctuations. For the question, we say that, okay, fine, this is our charge neutrality point. This is the open band gap. I have got edge states, and my transport is through those edge states. I am putting my Fermi energy right in the middle. Now, suppose I change my Fermi energy slightly from there, but not all the way to the band gap. If I change slightly here, from here, then it should not change the conductance at all, as long as the Fermi energy is within, sufficiently deep inside the band. So which means, shall we expect the mesoscopic fluctuations to actually be suppressed when the transport is through along the edges? So we tested it. Let me show you how we tested it. So this is a standard conductance versus density. So they're obviously around 0. This is at 60 millivolt of band gap. There's already a band gap, and this is as a function of density. So this is Fermi energy or density, and what I'm going to do is that I'm going to show you the experiment which shows around a particular point, if I vary the density slightly, how does the conductance change? This is how the mesoscopic conductance fluctuations behaves. So you can see that conductance behaves something like this. There is a random fluctuations of conductance somewhere here as around a small window around these points. What happens at this point is that it's very, very small, and at this point, just away from it, look at the conductance fluctuations. This is very large. So the conductance fluctuations seems to be picking up on both sides of the charge neutrality point, but at or around the charge neutrality point, the conductance fluctuation is strongly suppressed. If I take this, make this results and plot it for all densities, the conductance fluctuations look something like this. That this is red one is the conductance, and blue part is the conductance fluctuations as you go nearer to the. Somewhere here, probably somewhere close, it is not the band gap, I'm going to show you in the next slide. Close to the band gap, the conductance fluctuation dramatically drops, nearly goes to 0. Even though the conductance is varying slowly, the fluctuation goes dramatically straight to 0. And this is something which gave us some sort of a confidence that whether the kind of transport that we're looking is probably the topological transport around the edges and not some weird bulk transport. Okay, this is my last slide. One more. I'm show you what kind of behavior of conductance fluctuations that we get for various electric fields or various kinds of band gaps. You can see in all cases, the conductance fluctuation tries to go up as the system is becoming more and more insulating as a function of Fermi energy. But the moment it comes very close to the charge neutrality point, it shows immediate decrease and goes sometimes very small, sometimes 0, sometimes not entirely 0, but it always shows a dip and a minimum near the charge neutrality point, probably indicating that there is a strong topological component in near the charge neutrality. I'd like to summarize. We have now found a short channel bilayer graphene and which show exponential increase in resistance, and the band gap extrapolates to not the band gap, should be resistance, extrapolates to 4e square by 8 at 0 band gap. Mesoscopic noise decreases to 0 roughly around the same point. So is this an evidence of the edge transport? I would like to thank your attention.
Questions?